Hello, yeah, welcome to our next series of lectures on differential equations. So in this lecture, I'm going to continue with first order. Well, I'm going to start with first order differential equations. We've already looked at the definition of what a differential equation is, some terminologies, and I gave you a motivation for why differential equations are important. Um, in this particular lecture, we'll take a look at separable equations, linear first order equations, exact equations, and then substitutions and transformations. This is like different first order equations that we can use different methods to solve. Okay, so this is going to cover a couple of videos, maybe 2 or 3 videos. So watch out for other videos on first order differential equations. Okay, so a separable first order differential equation is an equation of this form, like dy dx is equal to a function of x and y. Okay, now it is separable if this f here can be written in the form h of y times g of x. In other words, we can separate this right hand side is a function, if you like, of only y and a function of only x. If that is the case, then we call this differential equation separable. Okay, you see a lot of it, so pay attention. Separable equations are quite common. So I'll do a series of examples on this. So you should pay attention to that. Okay, so to solve a separable equation of this form, the reason why we call them separable is that we can separate the y's and the x. Y's will like on one side of the equation and the x's on the other side, or one variable on one side and another variable on the other side. Okay, so in this case, I can divide through by, if you like, h of y and take the x to this side, and I get this equation. So I have my y's on the left and then the x's on the right hand side. Of course, we are assuming that h of y is not 0 because otherwise this will not be defined. Okay, so you need this condition. Well, there are times that this h equals y, h of y equals 0 could actually be a solution to the differential equation, but you need this condition in order to solve that. All right, so you can always get the solution back, h of y equals 0, by inspecting the differential equation. Okay, that is the detail. But once you separate variables, then you can integrate both sides of the equation. Okay, so integrate this and that. And then the result of your integration then gives you the solution to the differential equation. Okay, basically that is the procedure for solving a separable differential equation. Okay, so let's look at a couple of examples, a series of them. Here's one, dy dx is equal to 1 over xy cubed. This is separable because I can multiply through by y cubed. I can take the x to this side, and I get y cubed dy is equal to the x all over x. Okay, so I've been able to separate the y's and the x's. Now I can integrate both sides to get this. So now it's quite straightforward. We know how to integrate expressions like this. That gives me 1 over 4 y raised to the power 4 is equal to, this is just ln x plus a constant of integration. I can multiply through by 4. I get that. This is just another constant, so let's call it c. Okay, so I can solve for y. Just find the fourth root of both sides and you get y is equal to this expression here as a solution. Well, in the first introduction to differential equations, we're able to show we're able to verify whether a given function is a solution to a differential equation. So basically, you can, once you get the solution, you can verify that if you want to, right? You can plug this into this equation to see whether the left hand side is equal to the right hand side. Okay, so that is a solution to this differential equation. Here's another one, dy dx is equal to y times 2 plus sine x. Again, this is separable. This is like our h of y, and 2 plus sine x is like our g of x. So, you know, it's easily separable. So I just divide through by y, and I take the x to this side of the equation and integrate both sides, and I get these expressions here. Okay, we can integrate this, that is just ln y. we know how to integrate that. That is 2x minus cosine of x plus c1. Okay. Um, if I want to separate y, I mean I can raise both sides to the power to e, right? To get y. So y is equal to exponents e raised to all of this. E to this constant is just another constant which I'm calling k. Okay. So I mean from here is all algebra. Once you integrate it, you get this. So y is equal to this is a solution to the differential equation. Okay. We'll look at these other example. I have this 1 plus x dy minus y dx is 0. Now it's not put in the form dy dx is equal to something, right? So you would have to rearrange it in separate variables if it's separable. Okay, so I can take this expression to this side of the equation and divide through by y and divide through by 1 plus x, and I end up with this. Okay, so you can basically rewrite this to look like that, where I have separated variables. I integrate both sides, that is this side. Integrate this, that's ln y. Integrate this, that is ln of 1 plus x plus your constant of integration. Remember that if I bring this side, I'll get minus ln of 1 plus x. So ln a, remember ln a minus ln b is ln of a over b. Okay, so if you apply that from calculus 2 or calculus 1, then you get ln of y over 1 plus x is equal to c1. All right, so now y over 1 plus x is equal to e raised to the power c1 plus or minus because of the absolute values here, right? All of this is now, let's call it some constant c. So y is equal to, if you like, c multiplied by 1 plus x, okay, as a solution. Where c here is now an arbitrary constant, not just a positive or a negative. It's any arbitrary constant, because note that over here, we need a condition that y is not equal to 0, right, in order to solve that. But in actual fact, y is equal to 0 is a solution to this, right? If you plug in y equals 0 here, this is 0, this is also 0. So the left-hand side is equal to the right-hand side. So y is equal to 0 is actually a solution. All right. Okay. I didn't put that condition here, but you need a condition that y is not equal to 0 and x is not equal to -1, right? For this to be defined. In any case, I mean, if you separate variables and integrate, you get your solution to be equal to that. Okay. So that's a solution to this equation here. Perhaps this is our last one, not sure, but let's solve this one. dy dx is equal to y squared minus 9. We can separate variables. Basically, you can divide through by this and bring your dx to the side, and then you get this dx, and then you integrate. All right. Again, we need a condition that y is not equal to plus or minus 3, otherwise this will not be defined. Okay. So if you remember how you integrate these this type of expressions from calculus 2, you can basically do this thing, use partial fractions, right? So write 1 over y squared minus 9 partial fractions. Okay, this is 1 over y minus 3 times y plus 3. Rewrite it as this is equivalent to this. Solve for a and b. A gives you 1 over 6, b gives you -1 over 6. I mean, I'm skipping all these steps because you have done this already. This is partial fractions, you know how to do that. Okay. So we know a, we know b. So we put them back here. So instead of integrating this, we can integrate these individual ones. That's the idea. Okay. So now, yeah, so this fraction is now this. So we integrate this is equal to the integral of the x. So if I integrate this, I can pull out 1 over 6, and this gives me ln y minus 3. I can pull out -1 over 6, and the integral of this gives me ln of y plus 3 is equal to, this is x plus a constant of integration. You can multiply through by 6. Because of the minus, you can basically divide this and that, right? So you have ln of y minus 3 over y plus 3 is equal to, because I multiply through by 6, I get 6x plus some other constant c2 is equal to this. All right. From here, again, you raise both sides to e. Yeah, so you take e raised to this powers, then you can solve for this expression y minus 3 over y plus 3 is equal to, this is e raised to the power 6s plus c2, but e to the power c2 is just, another constant multiplied by the e raised to the power 2x. Okay, and this is algebraic, right? You can solve for y, multiply through by this, group the y times, separate y out or isolate y, and then you get y is equal to 3 multiplied by all of that. Okay, good. So basically, you just have to try your hands on these examples again. Make sure that you understand each of these steps, or go through the algebraic part that probably skipped. Okay. So that was basically separable differential equations, first order equations. And as I said, you will find them quite common, often not in isolation. You'll be solving a problem and then here comes a separable differential equation, and then you just have to use these ideas to solve it. Okay. So in real life or in real applications, nobody will give you, hey, here is a separable differential equation, solve it, right? You solve some kind of a complex problem, and then part of the problem deals with a separable differential equation that you would have to solve. Okay, so keep that in mind. The next thing we'll do is we'll look at what is called linear first order equations. So what are linear first order differential equations? Well, is a differential equation of this form, a1 is function of x dy dx plus a2 a naught x times y, that is a naught as a function of x, okay, times y is equal to b as a function of x. All right, now if you divide through by this guy, suppose it's not equal to 0, you can put this in a form like this. This is called the standard form of the first order differential, the standard form of the first order linear differential equation, dy dx plus p of xy is equal to p of x. Okay, so remember this form. When you have an equation that looks like this, then you call it a first order linear first order. It's a linear first order equation. Okay, so the your dependent variable appears here as well. Note that if q is 0, for instance, if you bring this side, if this is 0 and you bring this expression here to the right hand side, you can basically separate it. So it becomes a separable differential equation. In the same way, it is if this expression is 0, then the resulting equation is also separable. Okay. Okay. So you need p of x and q of x to be non-zero. How do you solve equation 4? So we'll go through the procedure. All right. The procedure by which you can solve a linear first order equation. And you do that by what is called using an integrating factor method. That's what we're going to study here. The idea is that we want to suppose that this guy here, equation 4, could be simplified by multiplying it by some function of x. Let's call it mu of x. Okay, so suppose we multiply equation 4 by mu of x, we're going to end up with this equation. And now let's also suppose that this equation can be written as d dx of mu xy is equal to the right hand side mu x dx. Okay, so the idea is that if we can find a function, call it mu of x, if you can find it and multiply this equation through by it, then this thing could be reduced to this form. And if we knew what that function is, then we could easily integrate this to get our y, our solution. That is the whole idea behind this method. Okay. Okay. So question is, how do we actually find this mu of x? Note that this is basically separate from this. So to find, well, what I said is what I've written here, right? If we knew what mu x is, then it's easy to integrate this. Once we integrate both sides, then we can solve for y, as long as we know mu. Okay. So question is, how do we actually find this mu? Well, note that if we expand the left-hand side of equation 6, okay, if we expand this, we should get an expression, okay? And if we compare that expression we get after expanding this to the left-hand side of equation 5, then we get this equation here. We can show that the change in mu with respect to x is actually equal to mu p of x, okay? Again, I'll take it again. What I'm saying is that this is fine. If you expand this guy and compare the two equations, the left-hand sides, okay, then you can show that the change in mu with respect to x is actually equal to mu multiplied by p of x. Okay. Now note that this equation here is separable. Okay, once it's separable, you can divide through by mu, take the x to that side and integrate, and you have this. This is ln mu, so if I integrate this, I'm going to get mu of x to be equal to e raised to the power the integral of p of x dx. Okay. Again, some of these details you can find in my lecture notes. Okay, the lecture notes expands upon some of these ones, so read the notes as well, or or the textbook on this. So there are details on it. So the point is that we can solve for this integrating factor, which is the mu of x. So now that we know what mu of x is, we can go back, right, and just integrate this guy because we know what mu of x is. And then by doing that, we can pull out our y and get a solution. So that's what we are going to show next. So from equation 6, which I'm repeating here, I can integrate both sides, and I'll have mu x y is equal to the integral of mu of x q of x dx. I divide through by mu of x, and I'm going to get this. Okay, so as long as I know mu of x, q of x is known, if I'm able to integrate this, I have a solution to the differential equation. Once again, that mu of x is called the integrating factor. Okay, so that basically is the procedure. It is a procedure for solving linear first order differential equation. I've just written out the method by which you do that. I'll give you a summary of it just to recap so that you have a better understanding. So basically, these are the steps you follow to solve a linear first order differential equation. If the equation is not in standard form, make sure you first put it in the standard form to look like this. Okay, that's the first step. Then you compute what we call an integrating factor. Mu of x is equal to the integral of e raised to the power the integral of p of x dx. Your p of x is the coefficient of y here. Okay, good. Once you get the integrating factor, then next thing you do is that multiply all of this equation out by the integrating factor. Now, if your integrating factor is correct, in other words, if you did this thing correctly and you multiply through by through this equation by the integrating factor, you should end up with an equation that looks like this. In other words, if I expand the left-hand side here, it should be equal to the expression I get after multiplying this by the integrating factor. Okay. So again, second step, find the integrating factor, multiply equation 9 through by the integrating factor. When you do that, the left-hand side of this equation should become this, and the right-hand side, of course, is this because I have multiplied through by the integrating factor. So you should end up with an equation like this. Once you get this equation, integrate both sides of it and divide through by mu of x, and you end up with a solution to the differential equation, which is given by this. Okay. Now you can say that, well, can I just use this formula here? Yes, you could use it because you know mu of x, you have computed it, and you know k of x, you can do this. But it's better to know the procedure. All right. It's not a good idea to memorize formulas, right, if you don't have to. It's better to know the procedure, the method for doing it. That is easier to remember than memorizing formulas. Okay. But in any case, this gives you a form of solution to the linear first order differential equation. Okay, I hope I've made myself clear here. Let's do some examples to illustrate this. So here's a differential equation, dy dx plus 4y minus e to the negative x is equal to 0. And we are given an initial condition here. Y, when x is 0, y is 4 over 3. So this is a condition. So forget about this condition for now. Concentrate on this first, this equation here. It's linear. How do you know it's linear? Well, we write it like this. We can put it in a standard form by taking this to that side, right? When you do that, you have dy dx plus 4y is equal to e to the 4x. So our p is actually 4, and our k of x is this e to the negative x, okay? So which means I can compute the integrating factor to be equal to e raised to the power 4 dx. Remember, our p is now 4, so I have 4 dx. We can easily integrate this and I get e to the 4x. Again, when you integrate here, forget about the integrating factor because, I mean, it cancels out later on. So we usually don't add it. Okay, good. So now that you have your integrating factor, go back to the differential equation and multiply, okay, in the standard form, use the standard form, multiply through this equation by your integrating factor. When you do that, you get this equation here. Okay, now the right-hand side is fine. The left-hand side should be this ddx of your integrating factor multiplied by your y, your dependent variable. So that if you expand this, you should get this. Okay, if you expand this and you don't get that, of course, it means you did something wrong with computing the integrating factor. Good. Now that we have this, we just integrate both sides, and then this goes. So I have e to the 4x times y is equal to the integral of this. Integrate this and have 1 over 3 e to the 3x plus a constant of integration. Divide through by e to the 4x or multiply through by e to the minus 4x if you want. Then y is equal to this expression here. Okay, so basically this is a solution, but in this particular case, we are given the initial condition that when x is 0, y is equal to 4 over 3. So we can use this condition to find what the constant here, this arbitrary constant. We can use these conditions to find it. That's why it's given to you. Okay, so plug in x equals 0 and put y equals 4 over 3 and try to solve for c. Okay, so if you solve for c, you know that c is equal to 1. You put it back here, then your final solution, which is a particular solution, is y is equal to 1 over 3 e to the minus x plus e to the minus 4x. That gives you your solution to the differential equation. Okay, so that is one example. Let's do another one. We have x dy dx minus 4y is equal to x to the power 6 multiplied by e to the power e to the x. All right. Okay. Now, this is not in standard form, so you don't know if it's linear or not. So rewrite it to look like a standard first order linear equation. So what I do is that I divide through by x here. If you divide through by x, you're going to get this. Of course, you have to add this condition, otherwise this will not be defined, right? Good. So now it's in a standard form. This side, this thing is our q of x, right? And our p now is negative 4 over x. Okay, that's the p. And so to find the integrating factor is equal to e raised to the power the integral of negative 4 over x dx, right? Because this is our p now. And so we're going to get, note that you can just pull out negative 4 here. And the integral of 1 over x is ln x. So I have negative 4 ln x. I can take this up here, and I'll have e to the ln x to the negative 4, right? You can take negative 4 up there. Of course, the e and the ln cancels out, and your solution is e to the negative 4. I mean, x to the negative 4, sorry. Good. So we'll be able to get our integrating factor. The next step is that in your standard equation, multiply through by the integrating factor. And when you do that, you're going to get this. All right. X to the negative 4. Note that when you multiply x to the negative 4 by x to the 5, right, you're going to get x to the negative to the power 1. So that is why we have x here times the e to the x. So you get this equation. Once again, if you did this correctly, then the left-hand side should be the same as d dx of x to the negative 4y. Or if you like, if we expand this, you should get the left-hand side here. Okay, good. So now that we are here, all you do is that you integrate both sides of the equation. And you're going to have this x to the negative 4 times y is equal to this integral. If you remember from calculus 1, if you have an integral like this, you can basically use integration by parts, right, to integrate it. So I haven't done it here. So use integration by parts. When you integrate this, you're going to end up with this x e to the x minus e to the x plus c, okay, which you can rewrite like this. So we know this, we know how to integrate this. It's just this, which means x to the negative 4y is equal to that expression, okay? And now I can just multiply through by x to the 4, and I get y is equal to this as my solution, okay? Of course, with the arbitrary constant. Now we don't have an initial condition, so we just leave it as that. Okay. So basically, we've looked at how you solve a separable differential equation, first order equation, and we've also looked at how you solve a first order linear differential equation. Okay, these are the two methods we've tackled. But I'm going to end the video here. In my next video, also on first order equations, we'll proceed to look at exact equations, and then hopefully we can finish with substitutions and stuff, Bernoulli's equation and all of that. Okay, so I mean these are some exercises you can try your hands on. Okay, so in the next one we'll look at exact equations, and then we'll also start looking at substitutions and transformations. Okay. All right. All the best. So my next video is going to start from here.